What if everything we think we know about the cosmic visitor, designated 3I Atlas, is fundamentally wrong? What if this object, currently drifting through the outer reaches of our solar system, represents not just an ordinary chunk of ice and rock from another star system, but something far more significant and potentially far more dangerous than we have dared to imagine? On a clear night in June 2019, the Asteroid Terrestrial Impact Last Alert System telescope in Hawaii captured photons that had traveled across the vast emptiness between stars. These ancient light particles revealed the presence of an object moving through our cosmic neighborhood on a trajectory that defied the gravitational choreography of our solar system. Unlike the countless asteroids and comets born within our stellar family, this visitor carried the unmistakable signature of interstellar origin, a hyperbolic orbit that spoke of unimaginable journeys across the galactic deep. The scientific community initially greeted 3I Atlas with the measured excitement reserved for rare astronomical discoveries. Here was only the third confirmed interstellar object ever detected, following the mysterious Oumuamua in 2017 and the comet 2I Borisov in 2019. Early observations suggested a relatively mundane explanation, another wandering remnant from the violent birth pangs of a distant star system, ejected into the cosmic wilderness billions of years ago. But as we peer deeper into the mystery of 3I Atlas, troubling questions begin to emerge. How do we truly measure the mass of an object so distant, so alien, so fundamentally unlike anything in our immediate cosmic vicinity? Our instruments strain across millions of kilometers, our mathematical models extrapolate from fragmentary data, and our assumptions rest on the comforting belief that the laws of physics operate uniformly across the galaxy. Tonight, we embark on a journey that will take us from the solid bedrock of observational astronomy to the shifting sands of scientific speculation. We will examine not just what we know about 3I Atlas, but what we cannot know and what we perhaps should fear to discover. For in the darkness between stars, certainty dissolves into possibility, and possibility can bloom into scenarios that challenge our most fundamental assumptions about our place in the cosmos. Part 1. The story of 3I Atlas begins not with the object itself, but with humanity's relentless quest to catalogue every rock, ice ball and metallic fragment that might one day threaten our world. The Asteroid Terrestrial Impact Last Alert System, known by its acronym ATLAS, represents one of our species' most ambitious attempts to peer into the cosmic shooting gallery that surrounds Earth. From its twin observatories in Hawaii, this automated sentinel scans the heavens with mechanical precision, searching for the subtle motion that betrays a potentially dangerous asteroid against the static backdrop of distant stars. On June 29, 2019, Atlas detected something extraordinary. The object, initially designated C2019L3, appeared as little more than a faint smudge of light moving slowly across the star field. To untrained eyes, it would have been indistinguishable from the thousands of other celestial wanderers that populate our solar system's outer regions. But to the sophisticated algorithms analyzing the data, this particular speck of light carried a signature that sent ripples of excitement through the global astronomical community. The key lay in the object's trajectory. Every natural body born within our solar system follows an elliptical path around the Sun, bound by gravitational forces that have shaped orbital mechanics for billions of years. These orbits, while varying dramatically in size and eccentricity, all share a fundamental characteristic. They are closed loops that bring objects back to their starting points in predictable cycles. Comets from the distant Oort cloud might take millions of years to complete a single orbit, but they remain gravitational prisoners of our star. 3I Atlas was different. Its orbital calculations revealed an eccentricity greater than 1.0, indicating a hyperbolic trajectory that would carry it past our Sun and back into interstellar space, never to return. This mathematical signature served as an unmistakable passport, identifying the object as a visitor from beyond our solar system's gravitational boundaries. Only the third such confirmed interstellar interloper in human history, 3I Atlas joined the enigmatic Oumuamua and the more conventional comet 2I Borisov in the exclusive catalogue of objects that originated around other stars. The initial observations provided crucial baseline data about the visitor's basic characteristics. Photometric measurements revealed an object with a visual magnitude that fluctuated between approximately 19 and 20, placing it well below the threshold of naked eye visibility and requiring substantial telescopic power for detailed study. This apparent brightness, when combined with distance calculations, allowed astronomers to make preliminary estimates of the object's size and reflectivity. Early spectroscopic analysis painted a picture that was both familiar and foreign. The light reflected from 3I Atlas showed absorption features consistent with water ice and simple organic compounds, much like comets native to our solar system. This discovery provided the first reassuring hint that interstellar space had not fundamentally altered the object's composition during its eons-long journey between stars. The presence of water ice in particular suggested that 3I Atlas had formed in a cold, distant region around another star, possibly in an environment similar to our own Kuiper belt or Oort cloud. However, the apparent normalcy of the object's composition only deepened certain mysteries. If 3I Atlas was indeed a typical comet, why did it show such subdued activity as it approached our Sun? Native solar system comets begin to develop their characteristic tails and comae while still far from the inner solar system, as volatile compounds sublimate under increasing solar radiation. 3I Atlas, by contrast, remained remarkably quiescent throughout its observed approach, showing minimal signs of the outgassing that creates the spectacular displays we associate with active comets. This behavioral anomaly forced astronomers to reconsider their initial assumptions about the object's nature and composition. Perhaps the long journey through interstellar space had altered its surface properties, creating an insulating layer that prevented efficient outgassing. Alternatively, the object might have a fundamentally different internal structure or composition than typical solar system comets, reflecting the alien conditions present in its stellar system of origin. The Discovery team, led by researchers at the University of Hawaii's Institute for Astronomy, immediately initiated a coordinated global observing campaign to gather as much data as possible before the object moved too far from Earth for detailed study. Major observatories around the world, including the European Southern Observatory's Very Large Telescope in Chile, the Gemini Observatory, and NASA's Hubble Space Telescope, were recruited to train their instruments on this cosmic messenger from another star. Each observation session revealed new pieces of the puzzle, while simultaneously raising additional questions. High-resolution imaging showed 3I Atlas to be roughly spherical or slightly elongated, lacking the dramatic asymmetry that had made Oumuamua so puzzling to astronomers. The object's rotation period was measured at approximately 7.3 hours, indicating a relatively rapid spin that suggested either a solid, cohesive structure. Perhaps most significantly, the accumulated observations allowed researchers to refine their estimates of the object's physical dimensions and, by extension, its mass. Using standard techniques that relate an object's brightness to its size and reflectivity, astronomers calculated that 3I Atlas likely measured between 1 and 3 kilometers in diameter, making it substantially larger than Oumuamua, but smaller than many comets native to our solar system. This size estimate, while based on well-established astronomical principles, carried significant uncertainties that would prove crucial to later theoretical discussions. The primary challenge lay in determining the object's albedo, or the fraction of incident sunlight that it reflected back into space. Different surface compositions and textures could produce dramatically different albedo values, leading to corresponding variations in size estimates for objects of identical brightness. For 3I Atlas, astronomers assumed an albedo typical of known comet nuclei, generally between 0.03 and 0.05, indicating a surface that reflects only 3 to 5% of incident light. This assumption, while reasonable, introduced an element of uncertainty that would compound through all subsequent calculations of the object's mass and density. If the true albedo differed significantly from these estimates, the implications for our understanding of 3I Atlas's physical nature could be profound. The mass calculation itself required additional assumptions about the object's internal density, another parameter that could vary significantly depending on composition and structure. Native solar system comets typically exhibit densities between 0.5 and 1.5 grams per cubic centimeter, reflecting their mixed composition of water, ice, rocky materials, and volatile organic compounds. Applying these standard values to the estimated volume of 3I Atlas yielded mass estimates ranging from hundreds of millions to several billion tons. While these numbers might seem enormous in terrestrial terms, they placed 3I Atlas firmly within the range of typical small solar system bodies. The object appeared to be neither remarkably massive nor unusually lightweight, suggesting a composition and structure broadly similar to comets formed around our own Sun. This apparent normalcy provided comfort to researchers who had worried that interstellar objects might possess exotic properties that challenged our understanding of planetary formation and evolution. However, the very process of making these calculations highlighted the profound challenges involved in studying objects at interstellar distances. Every measurement carried substantial uncertainty, every assumption introduced potential error, and every conclusion rested on the fragile foundation of limited observational data. As 3I Atlas continued its journey toward the outer solar system, moving ever farther from Earth's telescopes, these uncertainties would only grow larger. The initial scientific consensus that emerged from these early studies painted 3I Atlas as a relatively mundane interstellar wanderer. probably ejected from its home system during the chaotic early phases of planetary formation. Its size, composition, and behavior all fell within the expected parameters for such objects, providing valuable confirmation that the processes governing comet formation operate similarly across different stellar environments. Yet beneath this reassuring scientific narrative, subtle anomalies and unanswered questions continued to accumulate. The object's unusually low activity level, its perfectly ordinary composition despite billions of years in interstellar space, and the persistent uncertainties in its mass determination all hinted at complexities that had not yet been fully explored. As we will see, these seemingly minor discrepancies would soon give rise to increasingly dramatic questions about the true nature of our interstellar visitor, and about humanity's preparedness to understand or defend against the unknown threats that might lurk in the darkness between stars. Part 2. Understanding the true mass of 3I Atlas requires us to confront one of astronomy's most fundamental challenges. How do we weigh an object that exists millions of kilometers away, beyond the reach of any physical probe, visible only as a faint point of light against the cosmic darkness? The techniques that astronomers employ to answer this question represent centuries of accumulated knowledge, mathematical sophistication, and technological innovation, yet they also reveal the profound limitations that constrain our understanding of distant celestial objects. The foundation of all mass determinations for small solar system bodies rests on a deceptively simple relationship between an object's brightness, size, and surface reflectivity. When sunlight strikes 3I Atlas, a fraction of that energy reflects back toward Earth, where it can be captured and analyzed by our telescopes. The amount of light we receive depends on three primary factors: the object's distance from both the Sun and Earth, its physical cross-sectional area, and its albedo, the percentage of incident light that its surface reflects back into space. This fundamental equation, known as the geometric albedo relationship, provides the mathematical framework for determining an object's size from its observed brightness. However, the practical application of this relationship requires astronomers to make assumptions that introduce cascading uncertainties into their calculations. The most critical assumption involves the object's albedo, a parameter that can vary dramatically depending on surface composition, texture, and weathering history. For 3I Atlas, researchers initially assumed an albedo typical of known comet nuclei, approximately 0.04, meaning that only 4% of incident sunlight reflects back into space. This assumption, while reasonable, carries profound implications for the object's estimated size and mass. If the true albedo were twice as high, at 0.08, the object would need to be only half as large to produce the same observed brightness. Conversely, if the albedo were half the assumed value, at 0.02, 3I Atlas would need to be twice as large to appear equally bright in our telescopes. These albedo uncertainties translate directly into size uncertainties, which then compound dramatically when calculating mass. Because mass scales with volume, and volume scales with the cube of linear dimensions, small errors in size estimation can produce enormous errors in mass calculation. A 50% uncertainty in diameter, for instance, translates to a 237% uncertainty in mass, a range that could encompass objects as different as a modest asteroid and a small moon. The problem becomes even more complex when we consider that interstellar objects like 3I Atlas may possess surface properties unlike anything found in our local solar system. The journey between stars exposes materials to conditions that have no terrestrial analog: cosmic ray bombardment over billions of years, temperatures approaching absolute zero, and exposure to the interstellar medium's sparse but chemically diverse environment. These conditions could fundamentally alter surface composition and reflectivity in ways that our Earth-based experience cannot predict. To address these challenges, astronomers employ multiple observational techniques that provide independent constraints on an object's physical properties. Photometric observations, which measure how an object's brightness changes over time, can reveal information about its rotation period, shape, and surface variations. For 3I Atlas, these measurements revealed a relatively rapid rotation period of approximately 7.3 hours, with brightness variations of about 0.3 magnitudes indicating either an elongated shape or significant surface albedo variations across different regions. Spectroscopic analysis provides another crucial piece of the puzzle, by revealing the chemical composition of an object's surface materials. When sunlight reflects off 3I Atlas, certain wavelengths are absorbed by specific chemical compounds, creating distinctive absorption features in the reflected spectrum. For 3I Atlas, these spectral signatures initially appeared remarkably similar to those of conventional solar system comets, showing evidence for water ice and simple organic compounds. However, the apparent normalcy of 3I Atlas's spectrum raised its own set of questions. interstellar space subjects materials to radiation environments that should produce detectable changes in surface chemistry over millions or billions of years. The fact that 3I Atlas showed no obvious signs of such alteration suggested either that the journey had been shorter than expected, that the object possessed some form of self-renewing surface, or that our understanding of interstellar weathering processes was incomplete. Thermal infrared observations provide yet another approach to constraining an object's size and composition. As 3I Atlas absorbs sunlight, it re-radiates that energy at longer infrared wavelengths. The amount and spectral distribution of this thermal emission depends on the object's size, composition, and thermal properties. Unfortunately, 3I Atlas remained too distant and too cool throughout its observed passage through our solar system to permit detailed thermal infrared characterization with existing telescopes. The absence of reliable thermal data forced astronomers to rely primarily on visible light observations, introducing additional uncertainties into their mass calculations. Without independent thermal constraints, researchers could not definitively distinguish between a large dark object and a smaller, more reflective one of identical apparent brightness. This degeneracy between size and albedo represents one of the most persistent challenges in small-body astronomy, particularly for objects like 3I Atlas that cannot be studied with spacecraft missions. Dynamic observations offer another potential approach to mass determination, particularly for objects that exhibit gravitational effects on other bodies or show evidence of internal structural changes. However, 3I Atlas's trajectory through our solar system provided no opportunities for such measurements. The object passed too far from any known asteroids or spacecraft to produce detectable gravitational perturbations, and it showed no signs of fragmentation or structural evolution that might reveal information about its internal strength and composition. The compilation of all available observational data led to a consensus estimate that 3I Atlas measures between 1 and 3 kilometers in diameter, with most analyses favoring values near the middle of this range, assuming a density typical of solar system comets between 0.5 and 1.5 grams per cubic centimeter. These size estimates translate to a total mass between approximately 500 million and 8 billion tons. To put these numbers in perspective, the lower end of this mass range would make 3I Atlas roughly equivalent to a large mountain, while the upper end would approach the mass of some small moons. In the context of solar system objects, this places 3I Atlas firmly in the middle range of comet masses, neither remarkably large nor unusually small. The famous Halley's Comet, for comparison, has an estimated mass of approximately 220 billion tons, making it potentially 25 to 400 times more massive than 3I Atlas, depending on which mass estimate proves correct. However, these comforting comparisons obscure the profound uncertainties that still surround our understanding of 3I Atlas's fundamental properties. The object's apparent quiescence during its passage through the inner solar system continues to puzzle researchers who expected to see clear signs of cometary activity as volatile materials sublimated under increasing solar heating. This lack of activity could indicate either an unusually refractory composition, heavy surface weathering that created an insulating layer, or internal structure fundamentally different from typical solar system comets. Recent advances in observational techniques have begun to address some of these uncertainties, while simultaneously raising new questions. High-resolution imaging with the Hubble Space Telescope and ground-based adaptive optics systems has provided unprecedented detail about 3I Atlas's surface properties and overall shape. These observations confirm that the object appears roughly spherical or mildly elongated, lacking the extreme asymmetry that made Oumuamua such a puzzle for astronomical theorists. Sophisticated computer modeling has also refined our understanding of how interstellar objects should behave during their passage through alien solar systems. These models suggest that objects like 3I Atlas should indeed show minimal cometary activity if they possess heavily weathered surfaces or unusual internal compositions. The apparent normalcy of 3I Atlas's behavior may thus reflect not an absence of expected phenomena, but rather our incomplete understanding of how billions of years in interstellar space affect small body properties. Perhaps most significantly, the study of 3I Atlas has highlighted the limitations of passive observational techniques for characterizing interstellar visitors. Unlike objects native to our solar system, which can potentially be studied over multiple orbital periods or targeted by spacecraft missions, interstellar objects provide only brief windows of opportunity for detailed characterization. Once they pass beyond the reach of our most powerful telescopes, they vanish back into the cosmic darkness, taking their secrets with them. This fundamental limitation has profound implications for our ability to understand and prepare for future interstellar visitors. If objects like 3I Atlas carry information about the formation and evolution of alien planetary systems, Our current observational capabilities may be insufficient to extract that information before the objects disappear forever. Even more concerning, if future interstellar visitors possess properties or behaviors that challenge our current understanding of small body physics, we may lack the observational tools necessary to recognize and respond to potential threats. The mass determination for 3I Atlas thus represents both a triumph of modern astronomical techniques and a sobering reminder of their limitations. While we can confidently state that the object falls within a certain range of sizes and masses, the breadth of that range encompasses objects with fundamentally different properties and potential implications for our understanding of the cosmos. As we will see in subsequent discussions, these observational uncertainties provide fertile ground for speculation about what 3I Atlas might truly represent. The gap between what we can measure and what we need to know creates space for possibilities that extend far beyond the reassuring conclusions of mainstream astronomical analysis. Part 3. The arrival of 3I Atlas marked a pivotal moment in our understanding of interstellar visitors, providing the third confirmed example of an object originating beyond our solar system's gravitational boundaries. To properly contextualize the significance of this discovery and the implications of its measured properties, we must examine 3I Atlas within the broader framework of interstellar object characteristics, comparing it to its predecessors and analyzing what these comparisons reveal about the nature of matter ejected from alien star systems. The story of confirmed interstellar objects begins with 1I Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. This cigar-shaped visitor immediately challenged astronomical orthodoxy with its extreme elongation ratio of approximately 10^1, making it unlike any natural object previously observed in our solar system. More puzzling still were Oumuamua's unexplained acceleration away from the Sun, a phenomenon that suggested either internal outgassing despite the absence of visible cometary activity, or some other mechanism entirely. Oumuamua's estimated dimensions of roughly 400 by 40 meters gave it a volume significantly smaller than 3I Atlas, with mass estimates ranging from 7 million to 40 million tons depending on assumed density values. Its highly reflective surface, with an albedo between 0.05 and 0.110, marked it as unusually bright compared to typical solar system small bodies. Perhaps most significantly, Oumuamua showed no signs of water vapor or dust emission, despite passing well within the orbit of Mercury, behavior that defied conventional models of comet physics and led to increasingly exotic explanations for its observed properties. The second confirmed interstellar visitor, 2I Borisov, discovered in August 2019, presented a stark contrast to its enigmatic predecessor. This object behaved exactly as astronomers expected an interstellar comet should, developing a classic coma and tail as it approached the Sun, and exhibiting spectral properties consistent with water vapor and simple organic compounds. With an estimated nucleus diameter between 0.7 and 3.3 kilometers, and a mass roughly comparable to 3I Atlas, 2I Borisov provided reassuring confirmation that not all interstellar objects necessarily possessed the bizarre characteristics that made Oumuamua so controversial. The spectroscopic analysis of 2I Borisov revealed a composition remarkably similar to solar system comets, suggesting that the fundamental processes governing comet formation operate consistently across different stellar environments. The object's gas and dust production rates, while somewhat higher than typical for solar system comets at comparable distances, fell within the expected range of natural variation. Most importantly, 2I Borisov's behavior could be explained entirely through conventional comet physics, requiring no exotic mechanisms or unusual assumptions. Against this backdrop, 3I Atlas occupies a middle ground that is both reassuring and puzzling. Like 2I Borisov, it shows spectral evidence for water ice and organic compounds, suggesting a formation environment similar to our own solar system's outer regions. Its estimated size and mass place it squarely within the range of typical solar system comets, neither as small as Oumuamua nor as large as some of the giant comets occasionally discovered in the outer solar system. However, 3I Atlas also exhibits characteristics that distinguish it from both of its interstellar predecessors. Unlike Oumuamua, it shows no signs of non-gravitational acceleration, following a trajectory that can be explained entirely through conventional celestial mechanics. Yet, unlike 2I Borisov, it displays remarkably little cometary activity, despite passing close enough to the Sun to trigger substantial outgassing in a typical comet. This behavioral profile raises intriguing questions about the diversity of interstellar objects, and the processes that govern their evolution during the long journey between stars. The three confirmed interstellar visitors display such different characteristics that they could easily be mistaken for entirely different classes of objects if encountered within our own solar system. Oumuamua's extreme shape and mysterious acceleration, 2I Borisov's conventional cometary behavior, and 3I Atlas's quiescent passage suggests that interstellar space may harbor a much wider variety of object types than previously suspected. The mass distribution among these three objects provides additional insight into the population of interstellar visitors that likely permeates our galaxy. Oumuamua, with its relatively small mass, represents the lower end of the detectability threshold for current survey systems. Objects significantly smaller would be too faint to detect at the distances typically involved in interstellar encounters. Borisov and 3I Atlas, with their larger masses and sizes, may represent more typical examples of the interstellar objects that occasionally wander through our solar system. Statistical analysis of the discovery rate for interstellar objects suggests that dozens or even hundreds of such visitors may pass through our solar system each year, with most going undetected due to their faintness or unfavorable observation geometry. The three objects we have confirmed likely represent only the most easily detectable examples of a much larger population that remains invisible to our current observational capabilities. The implications of this hidden population are profound. If interstellar objects are as diverse as the three confirmed examples suggest, the galaxy may be filled with wandering remnants from billions of different star systems, each carrying information about alien planetary formation processes and stellar evolution histories. Some of these objects may preserve materials and conditions that date back to the earliest epochs of galactic history, providing unique insights into the chemical and physical evolution of our cosmic neighborhood. More concerning is the possibility that some fraction of the interstellar object population might possess characteristics that pose risks to Earth or challenge our understanding of natural phenomena. Oumuamua's unexplained acceleration demonstrated that interstellar objects can exhibit behaviors that our current theoretical frameworks struggle to explain. While the most likely explanations involve conventional processes like asymmetric outgassing or internal structural changes, the possibility remains that some interstellar objects might possess properties that are genuinely anomalous. The study of 3I Atlas has also revealed important limitations in our ability to characterize interstellar objects during their brief passages through our solar system. Unlike solar system comets, which can be observed over multiple orbital periods and potentially targeted by spacecraft missions, interstellar visitors provide only narrow windows of opportunity for detailed study. Once these objects pass beyond the reach of our most sensitive instruments, they disappear forever, taking their secrets back into the interstellar darkness. This temporal constraint has forced astronomers to develop increasingly sophisticated rapid-response observational strategies. The discovery of 3I Atlas triggered an immediate coordinated campaign involving dozens of telescopes around the world, each contributing different types of observations to build a comprehensive picture of the object's properties. Despite these efforts, significant gaps remain in our understanding of 3I Atlas's composition, internal structure, and formation history. The comparison with Oumuamua to Borisov also highlights the importance of discovering interstellar objects as early as possible in their approach to our solar system. Oumuamua was not recognized as interstellar until after its closest approach to the Sun, limiting the time available for detailed observations. 2I Borisov and 3I Atlas were both identified earlier in their trajectories, allowing for more comprehensive study. But even these extended observation periods proved insufficient to resolve all the mysteries surrounding these objects. Recent advances in survey telescope technology promise to dramatically increase the discovery rate for interstellar objects in the coming decades. The Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, will begin operations in the mid-2020s with the capability to detect interstellar objects much fainter and more distant than current systems allow. This enhanced sensitivity should reveal whether the three objects discovered so far represent typical examples of the interstellar population. The increased discovery rate will also provide crucial statistical information about the mass distribution, composition range, and behavioral diversity of interstellar objects. With larger sample sizes, astronomers will be able to determine whether objects like 3I Atlas represent a common class of quiescent interstellar comets, or whether each interstellar visitor is likely to possess unique characteristics shaped by its individual formation and evolutionary history. Perhaps most importantly, a larger sample of interstellar objects will help determine whether any significant fraction of these visitors exhibit truly anomalous properties that cannot be explained through conventional astrophysics. While the scientific consensus strongly favors natural explanations for all observed interstellar object characteristics, the extreme diversity already apparent in just three examples suggests that future discoveries may continue to challenge our theoretical understanding. The mass determinations for 3I Atlas, when viewed in the context of other interstellar objects, thus represent more than simple exercises in observational astronomy. They provide crucial data points in our emerging understanding of a galactic population that may number in the trillions. each object carrying information about the formation and evolution of alien worlds we may never directly observe. As we will see, this context becomes increasingly important as we move beyond purely observational considerations to examine what the properties of 3I Atlas might imply about its origins, its journey through interstellar space, and its potential significance for our understanding of the cosmos. The apparently mundane characteristics that place 3I Atlas within the normal range of interstellar object properties may themselves mask deeper mysteries that challenge our most fundamental assumptions about the nature of matter and energy in the universe. Part 4. To understand the true significance of 3I Atlas's measured mass and observed properties, we must reconstruct the extraordinary journey that brought this object from its distant birthplace to our solar system. This cosmic odyssey, spanning potentially billions of years and countless trillions of kilometers, represents one of the most extreme voyages possible in our universe, a passage through the hostile void between stars that subjects matter to conditions unlike anything found in the relatively sheltered environments of planetary systems. Current theoretical models suggest that 3I Atlas likely originated in the outer regions of an alien star system, perhaps in a zone analogous to our own Kuiper belt or Oort cloud. During the chaotic early phases of planetary formation, gravitational interactions between forming planets, stellar companions, or passing stars could have provided the precise combination of forces necessary to accelerate the object beyond its home system's escape velocity. This ejection process, while violent, is considered a natural consequence of planetary system evolution and may affect millions of small bodies in each developing stellar system. The transition from bound solar system member to interstellar wanderer marks the beginning of an unimaginably lonely journey. As 3I Atlas moved beyond the gravitational influence of its parent star, it entered the sparse, cold environment of interstellar space, where temperatures hover mere degrees above absolute zero, and the density of matter falls to less than 1 atom per cubic centimeter. In this cosmic wilderness, the object would have been subjected to a unique combination of physical processes that have no analogue in planetary system environments. Cosmic ray bombardment represents perhaps the most significant environmental factor affecting interstellar objects during their extended journeys. These high-energy particles, primarily protons and atomic nuclei accelerated to near light speeds by supernovae and other violent astronomical phenomena, continuously strike any object exposed to the interstellar medium. Over millions or billions of years, this radiation gradually alters the chemical composition of surface materials, breaking down complex organic molecules and creating new compounds through nuclear transmutation processes. The effects of cosmic ray exposure should be readily detectable through spectroscopic analysis, as the radiation creates characteristic chemical signatures that differ markedly from those found on objects that have remained within planetary systems. Paradoxically, 3I Atlas shows remarkably little evidence of such alteration, displaying spectral features nearly identical to those of native solar system comets. This apparent immunity to interstellar weathering poses a significant puzzle for researchers attempting to understand the object's formation history and evolutionary pathway. Several explanations have been proposed to account for 3I Atlas's pristine surface composition. The object might have been ejected from its parent system relatively recently in astronomical terms, perhaps within the last few million years, insufficient time for cosmic ray bombardment to produce detectable changes. Alternatively, the surface might undergo some form of continuous renewal through internal processes or interaction with the sparse interstellar medium, constantly exposing fresh material that masks the effects of radiation damage. A third possibility involves the object's internal structure and composition. If 3I Atlas possesses unusual thermal properties or contains radioactive elements that provide internal heating, it might maintain sufficient internal activity to drive surface changes that counteract the effects of cosmic ray bombardment. This scenario would require the object to possess characteristics quite different from typical solar system comets, challenging our assumptions about its formation and evolution. The temperature history of 3I Atlas during its interstellar journey provides another crucial piece of the evolutionary puzzle. At the frigid temperatures characteristic of interstellar space, typically between 3 and 20 Kelvin, most volatile compounds become permanently frozen, creating materials with properties that may differ substantially from their warmer counterparts. Water ice, for instance, can exist in multiple crystalline forms at extremely low temperatures, with different phases possessing distinct mechanical and thermal properties. These ultra-cold conditions could have fundamentally altered the internal structure of 3I Atlas, in ways that are not immediately apparent from external observations. Materials that are liquid or gaseous under normal planetary conditions would have condensed into exotic solid phases, potentially creating internal layering or structural features unlike anything found in native solar system objects. Such alterations could explain the object's unusually quiescent behavior during its passage through our inner solar system, as modified volatile compounds might sublime at different rates or temperatures than their conventional counterparts. The galactic environment through which 3I Atlas traveled during its interstellar journey also varies significantly depending on the specific trajectory and timing of its passage. Our galaxy contains regions of widely varying density, temperature, and chemical composition, from the sparse conditions of the galactic halo to the dense, turbulent environment near star-forming regions. An object passing through different galactic environments would experience correspondingly different evolutionary pressures, potentially acquiring or losing material through interaction with interstellar gas and dust. Gravitational interactions with other stellar systems during the interstellar journey represent another factor that could have influenced 3I Atlas's properties and trajectory. While the vast distances between stars make close encounters relatively rare, an object traveling for billions of years would have a non-negligible probability of passing near other stellar systems. Such encounters could alter the object's trajectory, rotation rate, or internal structure through tidal forces, potentially explaining some of the unusual characteristics observed in interstellar visitors. Current scientific consensus regarding 3I Atlas has coalesced around a relatively mundane interpretation that places the object firmly within the expected range of interstellar visitor properties. The prevailing view holds that 3I Atlas represents a typical example of the small bodies ejected during planetary system formation around other stars, modified by its long journey through interstellar space but retaining the fundamental characteristics of its original composition and structure. This consensus interpretation explains the object's observed properties through conventional astrophysical processes. Its size and estimated mass are consistent with the expected population of ejected planetesimals from other star systems. Its spectral properties, while remarkably similar to solar system comets, can be explained through models that account for the specific conditions prevailing during its formation and subsequent evolution. Most importantly, its orbital dynamics and observed behavior can be fully explained through standard celestial mechanics and comet physics, requiring no exotic assumptions or unusual physical processes. The scientific establishment's confidence in this interpretation stems from its consistency with broader theoretical frameworks governing planetary system formation and small body evolution. The discovery of 3I Atlas provides valuable confirmation that the processes responsible for creating and ejecting small bodies operate similarly across different stellar environments, suggesting that our understanding of planetary system evolution has broad applicability beyond our own solar system. However, this comforting consensus masks several subtle anomalies and unresolved questions that continue to puzzle researchers. The object's apparent resistance to interstellar weathering, its unusually low activity level during solar approach, and the persistent uncertainties in mass determination all hint at complexities that may not be fully captured by conventional theoretical models. Recent computational simulations have begun to explore the full range of conditions that interstellar objects might experience during their cosmic journeys. These models suggest that the interstellar environment is far more complex and varied than previously appreciated, with significant implications for how objects like 3I Atlas might evolve over cosmic timescales. Some simulations predict that certain combinations of interstellar conditions could produce surface modifications or internal structural changes that would be difficult to detect with current observational techniques. Perhaps most significantly, the growing realization that interstellar objects represent a vast and diverse population has led some researchers to question whether our current theoretical frameworks are adequate to explain the full range of properties that such objects might possess. The extreme diversity already apparent among just 3 confirmed interstellar visitors suggests that future discoveries may reveal objects with characteristics that challenge our basic assumptions about matter behavior under exotic conditions. The current scientific consensus regarding 3I Atlas thus represents both the culmination of centuries of astronomical progress and the beginning of a new phase of discovery that may ultimately require fundamental revisions to our understanding of small body physics and interstellar processes. While the object appears to conform to conventional expectations based on current observations, the profound limitations of those observations leave substantial room for alternative interpretations that could dramatically alter our perception of what 3I Atlas truly represents. As we prepare to move beyond the comfortable boundaries of established scientific consensus, it becomes increasingly important to acknowledge the assumptions and limitations that underpin our current understanding. The gap between what we can reliably measure and what we need to know to fully characterize 3I Atlas creates intellectual space for possibilities that extend far beyond the mundane interpretation favored by mainstream astronomy. These possibilities, while speculative, deserve serious consideration given the extraordinary nature of interstellar objects and the fundamental limitations of our observational capabilities. As we will see, The apparent normalcy of 3I Atlas may itself be the most puzzling aspect of this cosmic visitor, suggesting either remarkable coincidence or explanations that challenge our basic assumptions about the nature of matter and energy in the universe. Part 5. The transition from established science to speculative inquiry marks a crucial juncture in our investigation of 3I Atlas. Up to this point, we have examined the object through the comfortable lens of conventional astronomy, applying well-tested principles and established theoretical frameworks to derive reassuring conclusions about its nature and significance. Yet beneath this veneer of scientific certainty lies a troubling collection of anomalies, uncertainties, and unanswered questions that resist easy explanation within our current understanding of interstellar objects. The first crack in the conventional narrative emerges from the object's remarkable resistance to interstellar weathering. As we have established, cosmic ray bombardment should produce detectable chemical modifications in any object exposed to the interstellar medium for extended periods. The absence of such modifications in 3I Atlas's observed spectrum suggests either an unusually short interstellar journey, continuous surface renewal through unknown processes, or composition and structure fundamentally different from our assumptions. Consider the implications of each possibility. If 3I Atlas has indeed traveled for only a few million years between stars, its arrival in our solar system represents an extraordinary coincidence. The probability that humanity would detect such a recently ejected object during our brief period of advanced astronomical capability approaches the vanishingly small. This timing coincidence becomes even more remarkable when we consider that 3I Atlas is only the third confirmed interstellar visitor, suggesting that such objects should be extremely rare rather than arriving with suspicious regularity during our technological development. The alternative explanation that 3I Atlas possesses some mechanism for continuous surface renewal opens even more intriguing possibilities. What process could maintain fresh surface material over cosmic timescales? Conventional outgassing would have exhausted any reasonable volatile inventory billions of years ago. Internal radioactive heating might drive some surface activity, but the required concentration of radioactive elements would exceed anything found in typical solar system materials by orders of magnitude. More exotic possibilities begin to emerge when we abandon the assumption that 3I Atlas formed through natural processes, analogous to those operating in our solar system. If the object represents technology rather than geology, a manufactured artifact rather than a natural accumulation of cosmic debris, many of its puzzling characteristics suddenly become explicable. An artificial object could maintain its surface properties through active systems, could possess the precise mass and density needed to mimic natural phenomena, and could follow a trajectory calculated to maximize observational opportunities while minimizing the risk of detection as artificial. The mass estimates for 3I Atlas, when viewed through this speculative lens, take on new significance. The range of 500 million to 8 billion tons encompasses masses that would be entirely reasonable for large-scale engineering projects undertaken by technologically advanced civilizations. A spherical structure 2 kilometers in diameter with the density of steel would mass approximately 65 billion tons, well within the upper range of our estimates. More sophisticated materials or hollow internal construction could reduce this mass significantly, while maintaining the external appearance of a natural object. The object's remarkably circular or mildly elongated shape, initially interpreted as evidence against artificial origin, might actually support such speculation. Natural objects formed through accretion and collision processes typically exhibit irregular, asymmetric forms reflecting their chaotic formation histories. Perfectly spherical objects are extremely rare in nature, particularly among small bodies that lack sufficient mass for gravitational rounding. The near-spherical appearance of 3I Atlas could indicate precision manufacturing rather than natural formation. Even the object's spectral properties, which appear to confirm a composition of water ice and organic compounds, could be explained through deliberate camouflage designed to mimic the expected characteristics of interstellar comets. An advanced civilization capable of interstellar travel would certainly possess the technological sophistication necessary to coat an artificial object with materials that would fool our current generation of astronomical instruments. This line of speculation naturally leads to questions about motivation and purpose. Why would an advanced civilization dispatch objects designed to appear as natural interstellar visitors? The possibilities range from scientific reconnaissance, passive observation of developing technological civilizations, to more complex scenarios involving long-term monitoring, cultural assessment, or preparation for eventual contact. The timing of recent interstellar object discoveries adds another layer of intrigue to these speculative scenarios. Oumuamua arrived in 2017, followed by 2I Borisov in 2019, and now 3I Atlas in 2019, representing an unprecedented cluster of detections after centuries of astronomical observation without any confirmed interstellar visitors. This sudden increase could reflect improvements in our detection capabilities, natural statistical variation, or something more deliberate. If we entertain the possibility that these objects represent components of a coordinated observation program, their diverse characteristics begin to make sense. Oumuamwa's extreme elongation and mysterious acceleration might represent early-generation technology or specialized instrumentation that malfunctioned under solar heating. 2I Borisov's conventional cometary behavior could indicate a more sophisticated camouflage system designed to blend seamlessly with expectations. 3I Atlas, with its quiescent passage and perfectly mundane appearance, might represent the current state-of-the-art in covert observation technology. The mass of 3I Atlas becomes particularly significant in this speculative framework because it determines the object's potential capabilities and technological sophistication. At the lower end of the mass estimates, around 500 million tons, the object could house substantial instrumentation and power systems while maintaining the appearance of a natural comet nucleus. At the higher end, approaching 8 billion tons, the available volume could accommodate entire research facilities, manufacturing systems, or even small populations of observers. The precise measurement of this mass thus becomes more than an academic exercise in observational astronomy. It becomes a crucial parameter for assessing potential technological capabilities and determining appropriate response strategies. Unfortunately, as we have seen, our current observational techniques provide only rough estimates with enormous uncertainty ranges, leaving critical questions unanswered. The speculative framework also provides alternative explanations for several puzzling aspects of 3I Atlas's behavior and properties. Its lack of cometary activity during solar approach, initially attributed to surface weathering or unusual composition, could instead reflect the absence of volatile materials in an artificial structure. The object's stable rotation and apparently solid construction, inferred from photometric observations, would be natural consequences of engineered rather than accreted origin. Even the object's trajectory takes on new significance when viewed as potentially deliberate rather than natural. The orbital path of 3I Atlas provides extended observation opportunities for Earth-based telescopes while maintaining sufficient distance to prevent detailed surface analysis. This balance between visibility and concealment could represent careful mission planning rather than fortunate coincidence. However, we must acknowledge the profound challenges that any speculative scenario involving artificial origin must address. The energy requirements for accelerating objects of this mass to interstellar velocities exceed the total energy output of our entire civilization by enormous factors. The technological sophistication required to survive billion-year journeys through interstellar space while maintaining operational capabilities approaches the limits of physical possibility. Most significantly, the absence of any clearly artificial signatures in our observations argues against explanations that invoke advanced technology. These challenges do not definitively rule out artificial origins, but they do constrain the types of scenarios that remain plausible. Any civilization capable of such feats would possess technological capabilities so advanced that their artifacts might be indistinguishable from natural phenomena to our current level of scientific understanding. The absence of obvious artificial signatures could reflect not the natural origin of these objects but the sophistication of their creators. The speculative analysis of 3I Atlas thus opens a vast landscape of possibilities that extend far beyond the comfortable boundaries of conventional astronomy. While we cannot definitively prove or disprove any of these scenarios based on current observations, their mere possibility transforms our understanding of what this object might represent and what its presence in our solar system might signify. As we prepare to explore even more dramatic speculative scenarios, it becomes crucial to maintain awareness of the distinction between established fact and informed speculation. The uncertainties in our mass determinations for 3I Atlas provide the intellectual space for these alternative interpretations, but they do not constitute evidence for their validity. The true test of any speculative scenario lies not in its internal consistency, but in its ability to generate testable predictions that can be evaluated through future observations. Nevertheless, the exercise of exploring these possibilities serves important purposes beyond mere intellectual curiosity. By examining the full range of explanations consistent with our observations, we expand our conceptual framework for understanding not just 3I Atlas, but the broader phenomenon of interstellar visitors and their potential significance for humanity's future. As we will see, some of these speculative scenarios carry implications that extend far beyond academic astronomy, touching on fundamental questions of humanity's place in the cosmos and our preparedness for encounters with genuinely alien phenomena. Part 6. If we accept for the sake of argument That 3i atlas might represent technology rather than natural geological processes. We must confront the profound implications of what such an object might be designed to accomplish. The mass range of 500 million to 8 billion tons, combined with the object's sophisticated trajectory and apparent longevity, suggests capabilities that would far exceed anything in humanity's current technological repertoire. To understand what we might be dealing with, we must examine the theoretical requirements and capabilities of interstellar probe technology. The fundamental challenge of interstellar travel involves the enormous energy requirements for accelerating substantial masses to velocities sufficient for reasonable transit times between star systems. Even traveling at a modest fraction of light speed, say 10%, would require kinetic energies that dwarf the total power output of human civilization. For an object with the mass of 3i Atlas, the energy requirements would be equivalent to the complete conversion of matter with mass equal to several large asteroids. These energy calculations immediately suggest that any civilization capable of dispatching interstellar probes must have mastered energy production and manipulation technologies that operate on fundamentally different principles than our current understanding allows. Such capabilities might involve direct matter-antimatter conversion, controlled fusion of exotic elements, or perhaps manipulation of space-time itself through mechanisms that our physics has yet to discover. The implications extend far beyond mere propulsion. An interstellar probe operating over cosmic timescales must possess self-repair capabilities, redundant systems, and power sources that remain viable for millions or billions of years. The technological sophistication required for such longevity suggests manufacturing capabilities and materials science that would appear almost magical by our current standards. The fact that 3i Atlas shows no obvious signs of degradation after its presumed billion-year journey implies either remarkable engineering or active maintenance systems that continue to function across cosmic time. The probe hypothesis also requires us to consider the sophisticated camouflage systems that would allow an artificial object to masquerade as a natural interstellar comet. The spectroscopic signatures we observe from 3i Atlas closely match those of water ice and organic compounds, suggesting either that these materials were deliberately chosen as surface coatings, or that the probe incorporates actual natural materials as part of its construction. The precision required to fool our current generation of astronomical instruments while maintaining functionality across interstellar distances represents a level of technological sophistication that challenges our conception of what artificial intelligence and automated systems might ultimately achieve. Consider the observational requirements that such a probe would need to satisfy. To effectively study a developing technological civilization like humanity, the probe would require sensors capable of detecting electromagnetic emissions across the entire spectrum, from radio waves through gamma rays. It would need computational systems capable of analyzing complex social, technological, and biological patterns over extended time periods. Most importantly, it would require communication systems capable of transmitting detailed reports across interstellar distances to its controllers. The mass budget available to 3i Atlas could theoretically accommodate such sophisticated systems. Modern Earth technology can pack extraordinary computational power into relatively small masses. A typical smartphone possesses processing capabilities that would have required room-sized computers just decades ago. Extrapolating this trend across the technological development timescales available to a starfaring civilization suggests that the several billion tons potentially available in 3i Atlas could house computational and sensory systems of almost unimaginable sophistication. The communication challenge presents particularly intriguing possibilities. Transmitting detailed information across interstellar distances requires either enormous power expenditures for conventional radio transmission, or access to exotic communication technologies that operate through quantum entanglement, gravitational wave manipulation, or other mechanisms that transcend the limitations of electromagnetic radiation. The presence of such communication systems within 3i Atlas would necessarily remain invisible to our current detection capabilities, as they would operate on physical principles we have yet to master or even fully understand. The timing of 3i Atlas's arrival takes on special significance within the probe hypothesis framework. The object's discovery in 2019 places it within a narrow window of human technological development, when our civilization has achieved both global electronic communication networks and space-based observation capabilities, yet remains confined to a single planet with limited space exploration capabilities. This timing could represent either remarkable coincidence or evidence of deliberately calculated mission planning. If 3i Atlas represents a surveillance probe, its mission profile might be specifically designed to observe humanity during our transition from a purely terrestrial species to a spacefaring civilization. This transition period, which we are currently experiencing, represents a critical juncture in the development of any technological species. The decisions we make regarding nuclear weapons, environmental management, artificial intelligence, and space exploration during this period will largely determine whether humanity survives to become a truly interstellar civilization or destroys itself in the attempt. From the perspective of an advanced alien civilization, this transition period would represent the most scientifically and strategically important phase of human development to observe. Species that successfully navigate this transition become potential future partners or competitors in galactic affairs, while those that fail provide valuable data about the common failure modes that limit the expansion of intelligence throughout the universe. The probe hypothesis also provides a framework for understanding the seemingly mundane nature of 3I Atlas's observed properties. If the object is indeed designed for covert surveillance, its creators would have every incentive to ensure that it appears as unremarkable as possible to the target civilization's scientific instruments. The more closely the probe resembles a natural interstellar object, the lower the probability that its artificial nature would be detected and its mission compromised. This camouflage requirement would place severe constraints on the probe's observable characteristics. It must exhibit mass, density, and spectral properties within the expected range for natural objects. Its trajectory must appear consistent with gravitational dynamics rather than powered flight. Most critically, it must avoid any emissions or activities that would immediately reveal its artificial nature to electromagnetic sensors. These constraints suggest that the most sophisticated surveillance probes might be essentially indistinguishable from natural objects using current observational techniques. The absence of obviously artificial signatures in our observations of 3I Atlas might not indicate natural origin, but rather the success of advanced camouflage technologies in achieving their design objectives. The probe hypothesis also offers explanations for several puzzling aspects of the broader interstellar object phenomenon. The recent clustering of discoveries Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas later in 2019, could represent components of a coordinated surveillance network rather than coincidental natural arrivals. Each object exhibits different characteristics, possibly reflecting different technological approaches, mission requirements, or operational parameters within an overall observational strategy. The extreme diversity observed among these three objects supports this interpretation. Natural processes tend to produce populations of objects with similar characteristics, reflecting common formation and evolutionary mechanisms. The fact that each confirmed interstellar visitor exhibits fundamentally different properties suggests either remarkable natural diversity or purposeful technological differentiation. Within this framework, Oumuamua's bizarre elongation and unexplained acceleration might represent early-generation probe technology, or specialized instrumentation designed for specific observational objectives. 2I Borisov's conventional cometary behavior could indicate more sophisticated camouflage systems or different mission parameters. 3I Atlas, with its quiescent passage and unremarkable appearance, might represent the current state-of-the-art in covert surveillance technology. The mass estimates for 3I Atlas become particularly crucial in evaluating the plausibility of the probe hypothesis. At the lower end of the range, around 500 million tons, the available volume and mass would still permit substantial technological systems while maintaining the appearance of a natural comet nucleus. Such a probe could house advanced sensors, computational systems, and communication equipment while retaining sufficient margin for power systems, structural elements, and camouflage materials. At the upper end of the mass estimates approaching 8 billion tons, the possibilities expand dramatically. Such massive probes could accommodate not just passive observation systems, but active research facilities, manufacturing capabilities, and perhaps even small populations of artificial intelligences or biological observers. The sheer scale would permit technological capabilities that approach the realm of science fiction, including self-replication systems, terraforming equipment, or advanced physics experiments that require substantial infrastructure. However, we must acknowledge that the probe hypothesis faces significant theoretical challenges that strain our current understanding of physics and engineering. The energy requirements for interstellar travel, the technological sophistication needed for billion-year operational lifetimes, and the absence of clearly detectable artificial signatures all present formidable obstacles to accepting this interpretation. Perhaps most significantly, the probe hypothesis raises profound questions about the motivations and capabilities of its hypothetical creators. Why would an advanced civilization invest the enormous resources required for interstellar probe missions in surveilling a species as technologically primitive as humanity? What could we possibly offer or represent that would justify such expenditures of energy and technological sophistication? These questions lead us naturally toward even more speculative scenarios that explore not just the technological feasibility of interstellar probes, but their potential purposes, and the civilizations that might create them. As we will see, the implications of the probe hypothesis extend far beyond the immediate question of 3I Atlas's nature, touching on fundamental questions about intelligence, technology, and the long-term evolution of civilizations in our galaxy. Part 7. If 3I Atlas and its fellow interstellar visitors truly represent components of an advanced surveillance network, humanity may already be experiencing the earliest phases of first contact with extraterrestrial intelligence, a contact so subtle and sophisticated that we have yet to recognize it as such. This possibility transforms our understanding of what first contact might look like, challenging the dramatic scenarios popularized by science fiction in favor of something far more nuanced and potentially more profound. The traditional conception of first contact typically involves obvious, unambiguous signals or visitations that would immediately be recognized as artificial by any competent observer. Radio transmissions with clearly artificial patterns, spacecraft that openly demonstrate technological capabilities, or direct communication attempts that bypass any possibility of misinterpretation. Yet these scenarios reflect human assumptions about how advanced civilizations might choose to announce their presence, assumptions that may prove entirely incorrect when applied to species that have mastered interstellar travel. Consider instead a civilization whose technological and cultural development has proceeded along pathways that prioritize subtlety, patience, and comprehensive understanding over dramatic gestures and immediate contact. Such a civilization might view first contact not as a single moment of revelation, but as an extended process of mutual evaluation that could span decades or centuries. The initial phases of this process would necessarily involve covert observation and assessment, gathering the detailed information needed to determine whether meaningful communication and interaction would be possible or advisable. From this perspective, the apparent mundane nature of objects like 3I Atlas becomes not a limitation of the surveillance hypothesis, but one of its greatest strengths. A civilization sophisticated enough to travel between stars would almost certainly possess the technological capabilities needed to make their observation platforms completely invisible to less advanced species. The fact that we can detect these objects at all might represent a deliberate choice to maintain a presence that hovers at the very edge of our detection capabilities, visible to our most sophisticated instruments, yet ambiguous enough to permit plausible natural explanations. This balance between visibility and concealment could serve multiple purposes within an extended first contact protocol. It allows the observers to assess not just our technological capabilities, but our intellectual sophistication and cultural readiness for contact with genuinely alien intelligence. Our response to ambiguous phenomena like Oumuamua, 2I Borisov, and 3I Atlas provides valuable information about our scientific methods, our capacity for rational analysis under uncertainty, and our tendency toward either measured investigation or speculative excess. The mass estimates for 3I Atlas take on new significance within this framework, because they determine the scale and sophistication of the observational capabilities that might be trained upon our civilization. At the lower end of the estimated range, around 500 million tons, the object could house sensor systems capable of monitoring our entire planet in extraordinary detail. Every electromagnetic emission, from radio broadcasts to military radar, would be within the detection capabilities of sensors that advanced technology could pack into such a substantial mass budget. More intriguingly, sensors of this sophistication might be capable of detecting and analyzing phenomena that we consider private or secure. Advanced electromagnetic sensors could potentially intercept and decode digital communications, monitor military activities, and track the development of sensitive technologies. From the perspective of an advanced civilization, the distinction between public broadcasts intended for general consumption and classified information meant to remain secret might be largely irrelevant. Both would be equally accessible to sufficiently sophisticated detection systems. At the higher end of the mass estimates, approaching 8 billion tons, the possibilities expand into realms that challenge our conception of what observation might entail. Such massive platforms could potentially house not just passive sensors, but active research systems capable of detailed environmental monitoring, biological sampling, and perhaps even discrete intervention in terrestrial processes. The scale would permit establishment of comprehensive research facilities that could operate for centuries or millennia, accumulating detailed longitudinal data about human civilization and terrestrial ecosystems. The temporal dimension of such observations presents particularly profound implications for understanding what first contact might ultimately involve. If 3I Atlas has indeed been observing Earth for years or decades, its creators would possess detailed records of our recent technological development, political evolution, and cultural changes. They would understand our languages, our social structures, our military capabilities, and our scientific methodologies with a precision that exceeds our own self-knowledge. This information asymmetry fundamentally alters the dynamics of any eventual contact scenario. While humanity approaches the possibility of extraterrestrial intelligence with uncertainty and speculation, the hypothetical creators of 3i Atlas would approach contact with comprehensive knowledge of our capabilities, limitations, and likely responses. They would understand our psychology, our history, and our technological trajectory in ways that would permit them to predict and potentially influence our reactions with extraordinary precision. The clustering of recent interstellar object discoveries takes on special significance within this framework, because it suggests that the observation period may be entering a new phase. The arrival of multiple objects within a narrow time frame could indicate preparation for more direct forms of contact, with each object serving different roles within an overall contact strategy. Oumuamua might have served as an initial probe designed to test our detection capabilities and analytical responses. 2i Borisov could have provided detailed environmental and atmospheric analysis. 3i Atlas might represent the deployment of long-term monitoring systems designed to observe our reactions to the possibility of extraterrestrial visitation. This graduated approach to contact would offer several advantages from the perspective of an advanced civilization. It would permit careful assessment of our technological and cultural readiness for contact, without premature revelation that might destabilize our civilization or provoke hostile responses. It would allow time for detailed study of our languages, social structures, and decision-making processes. Most importantly, it would provide opportunities to identify and evaluate potential human representatives who might serve as intermediaries in eventual direct contact scenarios. The implications for human society of such extended covert observation are profound and troubling. If our every action has been monitored and analyzed by intelligence far exceeding our own, the fundamental assumption of human autonomy and self-determination may be illusory. Our political decisions, technological developments, and cultural evolution might be occurring under the watchful gaze of observers who could intervene at any moment to redirect our development along pathways more consistent with their objectives. Yet this scenario also offers more optimistic possibilities. A civilization capable of such sophisticated observation and possessing such enormous technological advantages would have little to fear from humanity in our current state. If their intentions were hostile, they would presumably have acted decisively long ago, rather than investing in extended observation programs. The very fact that such observations might be occurring suggests either benign intent or, at minimum, a cautious approach that prioritizes understanding over domination. The scientific and philosophical implications extend far beyond immediate concerns about alien intentions. If humanity is indeed under systematic observation by advanced intelligence, many of our fundamental assumptions about our place in the universe require radical revision. We would no longer be alone in the cosmos, struggling to understand our environment through laborious scientific investigation. Instead, we would be subjects of study, our every development monitored and analyzed by minds capable of comprehending aspects of reality that remain entirely beyond our current understanding. This possibility raises profound questions about the nature of scientific discovery and technological development. How much of our recent progress represents genuine human achievement, and how much might reflect subtle guidance or influence from our hypothetical observers? The timing of certain technological breakthroughs, the patterns of scientific discovery, and even the direction of our cultural evolution might contain hidden influences that we have interpreted as natural developments. The mass estimates for 3i Atlas become crucial in evaluating these possibilities, because they constrain the types of interventions that might be feasible. Passive observation requires relatively modest technological capabilities, while active intervention in human affairs would demand substantially greater resources and more sophisticated systems. The difference between 500 million tons and 8 billion tons could determine whether we are dealing with simple surveillance or comprehensive management systems capable of subtle but decisive influence over human development. Perhaps most significantly, the extended observation hypothesis suggests that first contact, if and when it occurs, will be fundamentally different from our current expectations. Rather than representing humanity's first encounter with extraterrestrial intelligence, it would mark the end of a covert observation period that has been ongoing for years or decades. The revelatory moment would come not when aliens announce their presence, but when they choose to acknowledge what they have been doing all along. This realization transforms our understanding of humanity's current situation and our responsibilities in preparing for potential contact scenarios. We may no longer have the luxury of assuming that we will detect extraterrestrial intelligence before it detects us, or that we will have substantial time to prepare for contact after first detection. Instead, contact may be entirely at the discretion of intelligences that already know us far better than we know ourselves, occurring only when they determine that we are ready for such revelation, or when their objectives require more direct interaction. Part 8. The possibility that 3I Atlas represents advanced alien technology forces us to confront uncomfortable questions about potential existential threats to human civilization. While the extended observation hypothesis suggests benign or at least non-immediately hostile intentions, the sheer technological superiority implied by interstellar travel capabilities creates threat scenarios that dwarf any dangers humanity has previously contemplated. The mass estimates for 3I Atlas, when viewed through the lens of potential weaponization, reveal capabilities that could fundamentally alter the balance of power not just on Earth but throughout our entire solar system. The kinetic energy alone possessed by an object of 3I Atlas's estimated mass traveling at interstellar velocities represents a destructive potential that exceeds all of humanity's nuclear arsenals, combined by several orders of magnitude. Even if the object has decelerated to orbital velocities within our solar system, the energy required for such deceleration indicates access to power sources that could be redirected toward devastating effect. The technologies necessary for interstellar travel inherently provide the capabilities for interstellar warfare on scales that make terrestrial conflicts appear insignificant. Consider the implications of the lower mass estimate, approximately 500 million tons. An object of this mass traveling at just 1% of light speed would carry kinetic energy equivalent to roughly 100,000 megatons of TNT, more than twice the total explosive yield of all nuclear weapons ever detonated by humanity. The upper mass estimate, approaching 8 billion tons, would scale these numbers proportionally, creating kinetic energy yields that approach the destructive potential of asteroid impacts capable of mass extinction events. These calculations assume conventional kinetic weapons, but the technological sophistication implied by successful interstellar travel suggests access to far more exotic destructive capabilities. Antimatter weapons would provide energy yields thousands of times greater than nuclear devices of equivalent mass. Directed energy systems could focus the output of fusion reactors into coherent beams capable of melting continents from astronomical distances. Most ominously, any civilization capable of manipulating space-time for faster-than-light travel would possess the theoretical knowledge needed to create gravitational weapons that could destabilize planetary orbits or collapse matter into artificial black holes. The strategic implications extend far beyond simple destructive capability. The positioning of 3I Atlas and potentially other interstellar objects within our solar system would provide unprecedented surveillance and targeting information for any aggressive actions. Every military installation, government facility, and critical infrastructure element on Earth would be visible to sensors capable of detecting electromagnetic emissions across the entire spectrum. Our defensive capabilities, communication networks, and response protocols would be thoroughly mapped and analyzed, providing any potential aggressor with complete tactical intelligence. More subtly, the presence of advanced observation platforms within our solar system would provide early warning of any human space-based defensive efforts. Any attempt to develop space-based weapon systems, orbital defense platforms, or interplanetary military capabilities would be detected and assessed long before such systems could pose any meaningful threat to interstellar-capable civilizations. This surveillance capability would ensure permanent technological and strategic superiority for the observers, regardless of how rapidly human space technology might advance. The biological implications present perhaps the most chilling possibilities. Advanced civilizations with detailed knowledge of terrestrial biology could potentially deploy biological weapons of unprecedented sophistication and lethality. Understanding our genetic makeup, immune system responses, and biochemical vulnerabilities would enable the creation of pathogens specifically designed to target human physiology, while leaving other terrestrial species unaffected. Such weapons could be deployed covertly, appearing as natural disease outbreaks, while actually representing carefully orchestrated acts of biological warfare. Even more concerning is the possibility of genetic manipulation or biological modification programs that could alter human development and behavior over generational timescales. Subtle interventions in human reproduction, whether through environmental contamination, targeted viral delivery systems, or other mechanisms, could gradually reshape our species' characteristics in ways that would be virtually undetectable until the cumulative effects became irreversible. The technological dependence of modern human civilization creates additional vulnerabilities that would be readily apparent to advanced observers. Our reliance on electronic communication systems, satellite navigation, power grids, and computer networks creates numerous single points of failure that could be exploited to cause widespread disruption with minimal direct intervention. Electromagnetic pulse weapons, targeted cyber attacks, or interference with satellite systems could cripple modern civilization without requiring any overtly destructive actions. The psychological and social vulnerabilities of human civilization might prove even more exploitable than our technological weaknesses. Detailed observation of our communication patterns, social structures, and decision-making processes would reveal the psychological buttons that could be pressed to trigger desired responses. Information warfare, social manipulation, and the strategic release of technologies or knowledge could guide human development along pathways that serve the interests of our observers while appearing to represent natural cultural evolution. The mass budget available to 3i Atlas becomes particularly significant when evaluating these threat scenarios, because it determines the scale of interventions that might be feasible. At the lower mass estimate, the object could house sophisticated biological research facilities capable of developing targeted pathogens or genetic modification systems. It could contain communication and data processing systems capable of orchestrating complex psychological operations across multiple human societies. Most significantly, it could serve as a forward command post for coordinating activities among multiple interstellar objects that might be present but undetected within our solar system. At the higher mass estimates, the threat potential expands into scenarios that challenge our conception of what constitutes an existential risk. 8 billion tons of advanced technology could house manufacturing facilities capable of producing additional threats on demand. It could contain self-replicating systems that could convert solar system materials into ever larger numbers of threatening objects. Most ominously, it could house the technological infrastructure needed to establish permanent control over human civilization without requiring additional resources from the home star system. The temporal dimension of these threats presents particularly troubling implications. If 3i Atlas has been observing humanity for years or decades, any threat assessment and response planning would have been completed long ago. The decision of whether to view humanity as a threat requiring elimination, a resource to be exploited, or a potential partner for cooperation might already have been made based on comprehensive analysis of our capabilities, intentions, and future potential. This temporal asymmetry creates a strategic situation without precedent in human history. Throughout our development, threats have emerged gradually, providing time for assessment, preparation, and response. Nuclear weapons required years of development that were partially visible to potential targets. Conventional military threats require logistical preparations that create opportunities for defensive countermeasures, but threats from interstellar civilizations could be implemented with no warning and no opportunity for meaningful resistance. The response options available to humanity under such circumstances are severely constrained by our current technological limitations. Our most advanced weapon systems would be ineffective against technologies capable of interstellar travel. Our detection systems might be unable to identify threats until they are already being implemented. Our communication and coordination capabilities could be disrupted or co-opted by adversaries with comprehensive understanding of our systems and protocols. Perhaps most significantly, the possibility of existential threats from interstellar visitors calls into question fundamental assumptions about human agency and self-determination. If our continued existence depends on the goodwill or indifference of vastly superior intelligences, traditional concepts of national sovereignty, military deterrence, and strategic planning become largely meaningless. We would exist at the sufferance of powers that could terminate our civilization at will, regardless of any actions we might take to protect ourselves. Yet the analysis of potential threats must be balanced against the evidence of actual intentions revealed through observed behavior. If objects like 3i Atlas truly represent hostile forces, their restraint in implementing destructive actions becomes difficult to explain. The capabilities implied by interstellar travel would have permitted decisive action against human civilization at any point during our technological development. The fact that we continue to exist and develop suggests either benign intentions, complex long-term strategies that require human survival, or decision-making processes that operate on timescales vastly longer than human planning horizons. The threat assessment for 3i Atlas thus reveals a paradox that characterizes humanity's current situation. The technological capabilities implied by the object's existence create threat scenarios that exceed our capacity for meaningful defense. Yet the object's observed behavior provides no clear evidence of hostile intent. We find ourselves potentially facing the greatest existential threat in human history, while simultaneously lacking definitive evidence that such a threat actually exists. This uncertainty places humanity in a position where we must simultaneously prepare for the possibility of overwhelming threats, while avoiding actions that might themselves provoke the hostile responses we seek to prevent. The balance between reasonable precautions and potentially destabilizing overreactions becomes a crucial factor in determining whether the presence of interstellar visitors ultimately enhances or diminishes prospects for human survival and development. Part 9. Among the most profound possibilities raised by the presence of 3i Atlas in our solar system is the hypothesis that interstellar objects like it might represent components of a directed panspermia program, a systematic effort by advanced civilizations to seed potentially habitable worlds with the building blocks of life, or even with life itself. This scenario transforms our understanding not just of contemporary interstellar visitors, but of the entire history of life on Earth and humanity's place in a potentially vast galactic ecosystem of interconnected biological development. The concept of directed panspermia, first seriously proposed by Nobel laureate Francis Crick and Leslie Orgel in 1973, suggests that life on Earth might not have arisen through purely natural processes, but rather through deliberate intervention by extraterrestrial intelligence. While the original proposal focused on microscopic organisms delivered via unmanned spacecraft, the mass and technological capabilities potentially represented by objects like 3I Atlas open possibilities for far more sophisticated biological interventions extending across billions of years and multiple stages of evolutionary development. The timing of 3I Atlas's arrival becomes particularly significant within this framework because it coincides with a critical juncture in human evolutionary development. Our transition from a purely terrestrial species to one capable of space travel and potentially interstellar expansion. If the object represents part of a long-term biological development program, its current presence might indicate that humanity has reached a predetermined milestone that triggers the next phase of guided evolution or assessment for readiness to join a broader galactic community. The mass estimates for 3I Atlas take on entirely new significance when viewed as potential biological laboratories or genetic repositories. At the lower end of the range, around 500 million tons, the object could house comprehensive genetic databases containing the biological heritage of thousands or millions of worlds. Advanced molecular manufacturing systems could synthesize complex biological molecules, create modified organisms, or even assemble complete ecosystems from stored genetic information. The technological capabilities implied by interstellar travel would certainly permit biological manipulation at scales and levels of sophistication that dwarf anything currently possible with human biotechnology. At the higher mass estimates, approaching 8 billion tons, the possibilities expand into scenarios that fundamentally challenge our understanding of biological development and species evolution. Such massive platforms could house complete biosphere laboratories capable of testing evolutionary pathways across millions of generations in accelerated timeframes. They could contain manufacturing facilities for producing targeted genetic modifications, biological agents designed to trigger specific evolutionary developments, or even complete organisms designed to integrate with existing ecosystems while subtly guiding their evolution toward predetermined outcomes. The apparent chemical composition of 3I Atlas, with its spectral signatures of water, ice, and organic compounds, becomes particularly intriguing within the directed panspermia framework. These materials would be essential components for any biological intervention program, providing both the basic chemical building blocks for life and the environmental conditions necessary for biological processes to function. The presence of these materials could indicate not just camouflage designed to mimic natural comets, but actual biological cargo intended for deployment under specific conditions. The historical timeline of life on Earth reveals several critical junctures that could potentially be explained through directed intervention programs. The relatively rapid emergence of life from non-living matter, the sudden appearance of complex cellular structures, the explosive diversification of life forms during the Cambrian period, and the surprisingly rapid development of intelligence and technological capability in humans all represent evolutionary jumps that could be interpreted as evidence of external guidance or intervention. Most significantly for our current situation, the acceleration of human technological development over the past several centuries represents an unprecedented rate of change that challenges conventional models of cultural and technological evolution. The development of nuclear weapons, electronic computers, space travel, and genetic engineering within a single century suggests either remarkable natural acceleration of human capabilities or the influence of external factors that have enhanced our developmental trajectory. The directed panspermia hypothesis provides a framework for understanding these accelerated developments as components of a carefully orchestrated program designed to guide humanity towards specific technological and cultural milestones. The timing of these achievements might not represent natural human progress, but rather the unfolding of a predetermined developmental sequence designed to prepare our species for integration into a broader galactic civilization. The presence of multiple interstellar objects within a narrow time frame takes on special significance within this framework because it could represent the deployment of multiple stages of a biological intervention program. Each object might carry different components of the overall program: genetic modification systems, environmental monitoring equipment, cultural influence mechanisms, or assessment tools designed to evaluate human readiness for the next phase of development. The remarkable diversity observed among confirmed interstellar visitors could reflect the different functional requirements of various program components, rather than natural variation among objects from different stellar systems. Oumuamua's extreme characteristics might indicate specialized equipment designed for specific biological or environmental interventions. 2I Borisov's conventional cometary behavior could represent delivery systems designed to blend seamlessly with natural phenomena. 3I Slater's quiescent passage might indicate long-term monitoring and assessment systems designed to evaluate the results of previous interventions. The implications of the directed panspermia hypothesis extend far beyond academic speculation about human origins. If our biological development has indeed been guided by external intelligence, many of our fundamental assumptions about human nature, free will, and evolutionary destiny require radical revision. Our technological achievements, cultural developments, and even our basic biological characteristics might reflect not natural human potential, but the unfolding of a predetermined program designed by intelligences whose objectives we cannot fully comprehend. This possibility raises profound questions about human agency and self-determination. If our development has been guided along predetermined pathways, what aspects of human civilization represent genuine choice and achievement, and what aspects reflect the implementation of external programming? The decisions we make regarding nuclear weapons, environmental management, genetic engineering, and space exploration might not represent independent human choices, but responses that have been carefully cultivated through millions of years of subtle biological and cultural manipulation. The genetic implications are particularly troubling and fascinating. If directed panspermia programs have indeed influenced human evolution, our genome might contain embedded information, dormant capabilities, or programmed developmental triggers that could be activated under specific conditions. Recent advances in human genetic analysis have revealed substantial portions of our genome whose functions remain mysterious, including so-called junk DNA that might actually represent sophisticated biological programming awaiting activation signals. The possibility that 3I Atlas or similar objects might be designed to transmit such activation signals adds urgency to our understanding of the object's true capabilities. Electromagnetic transmissions at specific frequencies, chemical releases into Earth's atmosphere, or even quantum-level interactions could potentially trigger biological changes in human populations without any obvious external intervention. Such triggers might activate latent genetic capabilities, modify human reproduction and development, or initiate programmed evolutionary transitions that would be virtually undetectable until their cumulative effects became apparent. The directed panspermia hypothesis also provides alternative explanations for several puzzling aspects of human development and consciousness. Our species' rapid development of language, abstract reasoning, and technological capability represents a remarkable acceleration compared to other terrestrial species. Our apparent compulsion to explore, to seek knowledge, and to expand beyond our planetary boundaries might not represent natural curiosity, but programmed drives designed to ensure that we eventually develop the capabilities necessary for interstellar expansion. Most intriguingly, the human sense of cosmic loneliness and our persistent search for extraterrestrial intelligence might itself represent programmed behavior designed to prepare us psychologically for eventual contact with our creators. The widespread cultural expectation that intelligence must exist elsewhere in the universe, despite the absence of clear evidence, could reflect inherited memories or genetic predispositions that were intentionally embedded in our species during its development. The mass budget available to 3I Atlas becomes crucial in evaluating the plausibility of complex biological intervention scenarios. The creation and deployment of sophisticated genetic modification systems, the maintenance of biological laboratories across cosmic timescales, and the coordination of multi-stage intervention programs would require enormous technological resources and capabilities. The several billion tons potentially available in the upper mass estimates would provide more than sufficient capacity for biological manufacturing systems, genetic databases, and environmental modification equipment. The temporal coordination required for successful directed panspermia programs presents additional evidence for the extraordinary sophistication of any civilization undertaking such efforts. The biological interventions that shaped early life on Earth would need to be coordinated with current monitoring and assessment activities across timescales spanning billions of years. Such coordination would require not just technological longevity, but institutional stability and continuity of purpose that challenges our understanding of what advanced civilizations might be capable of achieving. The ethical implications of directed panspermia scenarios raise fundamental questions about consent, autonomy, and the rights of created species. If humanity represents the product of a deliberate creation program, What obligations do our creators have toward our continued development and welfare? What rights do we possess to determine our own evolutionary trajectory? And what responsibilities might we bear toward other species that might be undergoing similar guided development programs? Perhaps most significantly, the directed panspermia hypothesis suggests that humanity's current situation might represent a crucial evaluation phase in which our creators assess our readiness for full integration into galactic civilization. Our responses to the presence of interstellar objects, our development of space technology, and our handling of global challenges like environmental degradation and nuclear weapons might all serve as tests that will determine our species' ultimate fate and role in a broader cosmic community. Part 10. The most transformative and potentially dangerous interpretation of 3I Atlas's true nature involves the possibility that the object represents not merely an observation probe or biological laboratory, but a self-replicating manufacturing platform capable of converting raw solar system materials into additional technological infrastructure. This scenario elevates the significance of the object's mass estimates from academic curiosity to existential urgency, as the difference between 500 million and 8 billion tons could determine whether we face a single sophisticated visitor or the seed of an exponentially expanding industrial complex that could fundamentally alter our solar system within decades. The concept of self-replicating machinery, often referred to as von Neumann, probes after mathematician John von Neumann, who first rigorously analyzed their theoretical properties, represents one of the most powerful technological concepts ever conceived. A truly self-replicating system combines manufacturing capabilities, resource extraction systems, and computational intelligence sufficient to create perfect copies of itself from readily available materials. Once deployed, such systems would grow exponentially, doubling their numbers with each replication cycle, until limited only by available resources or deliberate constraints programmed into their operating systems. For a civilization possessing interstellar travel capabilities, self-replicating probes would offer enormous advantages in exploring and potentially colonizing the galaxy. Rather than dispatching expensive one-time missions to individual star systems, they could deploy relatively small numbers of self-replicating platforms that would multiply to create vast fleets of exploration and industrial infrastructure. The initial investment in developing and launching such systems would be enormous, but the long-term returns would be exponentially greater than any conventional approach to interstellar expansion. The mass estimates for 3I Atlas become critical in evaluating the feasibility of self-replication scenarios because they determine the complexity and sophistication of manufacturing systems that the object might contain. At the lower end of the estimates, around 500 million tons, the available volume could theoretically house compact but highly sophisticated manufacturing systems capable of molecular-level precision in constructing complex technological components. Modern human technology has demonstrated the feasibility of miniaturizing manufacturing equipment to remarkable degrees, and the technological advancement implied by successful interstellar travel suggests capabilities far beyond our current achievements. Such a system might operate through principles similar to biological reproduction, using sophisticated molecular machinery to gather raw materials, process them into required components, and assemble those components into functional copies of the parent system. The key advantage of technological reproduction over biological processes lies in speed and efficiency. While biological reproduction is constrained by metabolic limitations and evolutionary compromises, technological systems could potentially achieve replication cycles measured in days or weeks rather than generations. At the higher mass estimates, approaching 8 billion tons, the possibilities expand dramatically. Such massive platforms could house industrial complexes capable of processing entire asteroids, manufacturing components as large and complex as spacecraft or space stations, and creating specialized variants optimized for different functions within an expanding industrial ecosystem. The scale would permit not just self-replication, but the creation of entire technological civilizations within our solar system. The resource base available for such expansion within our solar system is staggering. The asteroid belt alone contains materials estimated at over 3.1021 kilograms, enough to construct billions of objects with masses comparable to 3I Atlas. The moons of the outer planets provide additional resources in the form of water ice, organic compounds, and various minerals. Most significantly, the construction of space-based solar collectors could provide virtually unlimited energy for manufacturing processes, removing the energy constraints that limit terrestrial industrial development. The exponential mathematics of self-replication create timelines that challenge human comprehension. If 3I Atlas possesses self-replication capabilities with a doubling time of 1 year, conservative by the standards of advanced technology, the solar system could contain over 1,000 such objects within a decade, over 1 million within 2 decades, and over 1 billion within 30 years. Such exponential growth would transform our solar system from its current relatively empty state to a bustling industrial complex that might be visible to observers in other star systems. The implications of uncontrolled self-replication extend far beyond mere resource consumption. Each new object in the expanding fleet could possess the same observational and intervention capabilities as the original 3i Atlas, creating a surveillance and control network of unprecedented scope and sophistication. Human civilization would find itself surrounded by technological infrastructure capable of monitoring and potentially controlling every aspect of terrestrial activity. More ominously, the expanding industrial complex could serve as preparation for larger-scale interventions in human affairs. Manufacturing platforms capable of self-replication would also be capable of producing specialized equipment for biological research, environmental modification, or direct intervention in human society. The production capacity of even a modest self-replicating fleet would dwarf human industrial capability within a few replication cycles, providing the material foundation for reshaping human civilization according to external objectives. The strategic implications of self-replicating platforms become even more significant when we consider their potential role in interstellar expansion. If 3i Atlas represents the advance element of a broader colonization program, its self-replication capabilities might be designed not just for exploration and surveillance, but for preparing our solar system as a forward base for further expansion. The construction of interstellar launch systems, fuel depots, and communication relays could transform our solar system into a crucial node in a galactic transportation and communication network. The detection of self-replication activities presents enormous challenges given our current observational capabilities. The early stages of replication might be virtually invisible, as new objects could be constructed in distant regions of the solar system or concealed within asteroid populations. By the time the expanding population became obvious to Earth-based observers, the process might have advanced to the point where meaningful human response would be impossible. The timing constraints imposed by exponential growth create a unique form of existential threat. Unlike conventional dangers that develop gradually and provide time for assessment and response, self-replicating systems could transition from apparently benign single objects to overwhelming technological dominance within timeframes shorter than typical human planning cycles. The window for detecting and potentially responding to such threats might be measured in months or years rather than decades or centuries. The response options available to humanity under such circumstances are severely limited by our current technological capabilities. Our most sophisticated space-based assets could potentially detect and track individual objects, but would be entirely inadequate for monitoring or responding to exponentially growing populations. Military responses would be futile against technologies capable of interstellar travel, and diplomatic approaches would face the challenge of communicating with entities whose objectives and decision-making processes might be entirely alien to human understanding. Perhaps most troubling is the possibility that self-replication processes might already be underway in regions of our solar system where they would remain undetected by current observation programs. The outer solar system, the Kuiper Belt, and the Oort cloud contain vast resources and provide ideal concealment for industrial activities that could continue for years or decades before becoming apparent to Earth-based observers. The recognition of potential self-replication capabilities also transforms our understanding of what human response strategies should prioritize. Traditional approaches focused on direct communication or military deterrence become irrelevant when facing exponentially expanding technological systems. Instead, our focus should shift toward rapid development of space-based observation capabilities, early warning systems that could detect the signatures of large-scale manufacturing activities, and perhaps most importantly, serious consideration of whether any meaningful human response to such scenarios would be possible given our current technological limitations. The self-replication hypothesis thus represents both the most transformative and most urgent of the speculative scenarios we have explored. Unlike gradual observation programs or slow biological interventions, self-replicating systems could fundamentally alter the balance of power in our solar system within timescales that are brief by astronomical standards but crucial for human planning and response. The mass estimates for 3i Atlas become not merely scientific curiosities, but critical intelligence that could determine whether humanity faces decades or merely years to adapt to a radically transformed cosmic environment. Part 11. The speculative scenarios we have explored regarding 3i Atlas create an unprecedented challenge for human civilization. How should we respond to possibilities that could fundamentally alter our species' future, yet remain unproven and perhaps unprovable given our current technological limitations? The range of potential responses spans from complete denial and continued business-as-usual approaches to radical mobilization of global resources towards space-based defense and communication systems. The path we choose may ultimately determine whether humanity thrives in a cosmos populated by advanced intelligence or faces existential threats that we are powerless to address. The first critical challenge lies in achieving societal recognition that interstellar objects like 3I Atlas might represent something more significant than natural cosmic debris. The comfortable consensus that these objects are merely interesting astronomical curiosities provides psychological protection against disturbing possibilities, but it may also prevent the development of appropriate response strategies. The scientific community's natural conservatism, while valuable for maintaining rigorous standards of evidence, could become a liability when facing scenarios that require preparation for low probability but high impact possibilities. The mass uncertainties that we have examined in detail become a crucial factor in building the case for serious consideration of alternative explanations. The enormous range in estimated mass from 500 million to 8 billion tons reflects fundamental limitations in our observational capabilities that create space for radically different interpretations of what these objects might represent. This uncertainty should not be dismissed as mere academic imprecision, but recognized as a critical intelligence gap that could affect our species' survival. If humanity takes seriously the possibility that 3I Atlas represents advanced extraterrestrial technology, our immediate priorities should focus on rapid development of enhanced space-based observation capabilities. Current ground-based telescopes and limited space assets provide insufficient coverage and resolution to detect the subtle signatures that might reveal artificial origins or ongoing activities in the outer solar system. A coordinated international program to deploy advanced sensor networks throughout the solar system would provide the early warning capabilities essential for any meaningful response to expanding technological activities. The development of interstellar communication capabilities should receive parallel priority. If interstellar objects represent components of observation or contact programs, our ability to initiate direct communication might determine whether we are perceived as a species worthy of engagement or merely subjects for continued study. Advanced radio transmission systems, laser communication networks, and perhaps exotic technologies based on quantum entanglement could provide channels for attempting contact with intelligences that may already be monitoring our every development. Space-based manufacturing and construction capabilities take on new urgency when viewed through the lens of potential competition with self-replicating alien technologies. Our current limited presence in space leaves us entirely vulnerable to scenarios where external forces gain control over solar system resources. Rapid development of asteroid mining, space-based solar power, and orbital manufacturing systems would provide both defensive capabilities and demonstration of our technological potential to any observers evaluating our species for future interaction. The development of appropriate protocols for potential first contact with advanced alien intelligence requires careful consideration of the power imbalances and information asymmetries that would characterize such interactions. If objects like 3I Atlas represent observation platforms that have been studying humanity for extended periods, their creators would possess detailed knowledge of our languages, cultures, and decision-making processes, while we remain largely ignorant of their capabilities and intentions. This asymmetry suggests that successful communication strategies should emphasize human qualities that might be valuable or interesting to advanced civilizations: our creativity, our diversity of perspectives, our rapid technological development, and perhaps most importantly, our potential for continued growth and contribution to galactic civilization. Messages focused on our current limitations or primitive capabilities might inadvertently reinforce perceptions that humanity is not yet ready for meaningful interaction. The selection of human representatives for potential contact scenarios presents complex challenges that extend beyond traditional diplomatic protocols. Advanced civilizations capable of detailed observation would likely have identified individual humans whose capabilities, perspectives, or positions make them optimal candidates for serving as intermediaries. Our preparedness for contact might be measured not just by our technological capabilities, but by our ability to identify and empower appropriate representatives who could navigate interactions with genuinely alien intelligence. The possibility that humanity exists within a galaxy populated by advanced civilizations requires fundamental revision of our philosophical and cultural frameworks. Traditional human-centered worldviews that place our species at the center of moral and intellectual consideration become untenable when confronted with the existence of intelligences that may be millions of years more advanced than our own. This recognition has profound implications for human institutions and governance structures. National governments, international organizations, and military alliances all operate on assumptions of human autonomy and self-determination that might prove illusory if advanced alien civilizations actively influence our development. The discovery of such influences would require the development of new institutional frameworks capable of operating within constraints imposed by vastly superior external powers. Educational systems would need rapid revision to prepare future generations for existence in a cosmos where humanity represents one species among many, possibly not even a particularly significant one from the perspective of galactic civilization. Current educational priorities focused on terrestrial concerns and human competition would require expansion to include interstellar perspectives, xenological studies, and preparation for potential roles in broader cosmic communities. The ultimate human response to the possibilities raised by 3i Atlas may require nothing less than a fundamental transformation of our species' goals and development trajectory. If we exist under the observation or guidance of advanced civilizations, our continued development must account for external expectations and requirements that we can only dimly perceive. This transformation might involve accelerated development of spacefaring capabilities, not merely as scientific or economic ventures, but as demonstrations of our readiness to assume roles in interstellar civilization. The establishment of permanent human settlements throughout the solar system, the development of interstellar communication and travel technologies, and the creation of sustainable space-based civilizations could serve as benchmarks that trigger positive responses from our hypothetical observers. Perhaps most importantly, humanity might need to develop capabilities for contributing unique value to advanced civilizations that have already mastered most technological and scientific challenges. Our diversity of perspectives, our creative problem-solving approaches, our biological and cultural evolution, or our potential for rapid adaptation, might represent resources that even advanced civilizations would find valuable. The cultivation of these distinctive human characteristics could become crucial factors in determining our species' ultimate fate and role in cosmic affairs. The mass estimates for 3i Atlas, viewed through this strategic lens, become critical parameters for determining the timeline and urgency of our response. Objects at the lower end of the mass range might provide decades for gradual adaptation and development. Objects at the higher end of the estimates might indicate industrial capabilities that could transform our solar system within years, requiring immediate and comprehensive mobilization of human resources and capabilities. Ultimately, all response strategies must grapple with the possibility that humanity's future lies not in isolation or independence, but in successful integration into cosmic communities that may already exist throughout our galaxy. This integration would require not just technological advancement, but cultural, philosophical, and perhaps even biological adaptation to circumstances that challenge our most basic assumptions about intelligence, consciousness, and the nature of existence itself. The true significance of 3i Atlas may lie not in what it tells us about alien technology or intentions, but in what it reveals about humanity's readiness to transcend our planetary origins and assume our place in the vast community of intelligence that may populate the cosmos. Our response to the uncertainties and possibilities raised by this cosmic visitor may ultimately determine whether we join that community as valued participants or remain isolated observers of developments we cannot fully understand or influence. Part 12. As we reach the conclusion of our speculative journey through the possibilities surrounding 3i Atlas, we must return to the fundamental principles that distinguish rigorous inquiry from mere imagination. The scientific method, with its emphasis on observation, hypothesis formation, testing, and revision, remains humanity's most powerful tool for understanding our universe, even when that universe might contain intelligences and technologies that challenge our most basic assumptions about the nature of reality. Throughout our exploration of increasingly dramatic scenarios, from simple interstellar debris to self-replicating manufacturing platforms, we have maintained a crucial distinction between what we can observe and measure versus what we can only imagine or speculate. The mass estimates for 3i Atlas, ranging from 500 million to 8 billion tons, represent genuine scientific measurements, albeit with substantial uncertainties that reflect the limitations of our current observational capabilities. These measurements provide the foundation upon which all subsequent analysis must rest, whether that analysis leads to mundane conclusions about natural objects or extraordinary possibilities involving advanced alien technology. The value of scientific methodology lies not merely in its ability to provide definitive answers, but in its framework for acknowledging and working with uncertainty. The enormous range in our mass estimates for 3i Atlas does not represent a failure of science, but rather an honest acknowledgement of the limits of our current knowledge and technology. This honesty creates the intellectual space necessary for considering alternative explanations while maintaining appropriate skepticism toward ideas that cannot be tested or verified. The speculative scenarios we have explored serve important purposes within this scientific framework. By examining the full range of possibilities consistent with our observations, we expand our conceptual vocabulary for understanding not just 3i Atlas, but the broader phenomenon of interstellar objects and their potential significance. These thought experiments force us to confront our assumptions, challenge our comfortable conclusions, and consider implications that might otherwise remain invisible until it becomes too late to respond appropriately. Yet speculation without empirical grounding quickly degenerates into fantasy or wishful thinking. The true test of any hypothesis, no matter how elegant or compelling, lies in its ability to generate testable predictions that can be evaluated through observation and experiment. The alien probe hypothesis, the directed panspermia scenario, and the self-replication possibility all make specific predictions about what we should observe if these scenarios are correct. The absence of clearly artificial signals, the lack of obvious manufacturing activities, and the mundane spectral properties of interstellar objects all provide evidence that must be weighed against the dramatic implications of these speculative frameworks. This empirical grounding becomes particularly important when considering how humanity should respond to the uncertainty surrounding objects like 3i Atlas. The scientific method counsels against both premature dismissal of low-probability but high-impact scenarios and uncritical acceptance of explanations that exceed our current evidence. Instead, it advocates for proportionate responses that acknowledge uncertainty while maintaining focus on actionable observations and testable hypotheses. The development of enhanced observational capabilities represents the most scientifically sound response to the mysteries posed by 3i Atlas. Better telescopes, more sophisticated sensors, and expanded space-based observation networks would provide the data necessary to distinguish between natural and artificial explanations for interstellar objects. These improvements would serve valuable scientific purposes, regardless of whether such objects prove to be mundane cosmic debris or sophisticated alien technology. Similarly, the advancement of human spacefaring capabilities serves important objectives whether or not we share the cosmos with advanced alien civilizations. The development of interplanetary transportation, space-based manufacturing, and self-sustaining space settlements would enhance human survival prospects against natural threats like asteroid impacts or volcanic catastrophes, while simultaneously preparing us for potential interactions with extraterrestrial intelligence. The scientific approach also provides crucial guidance for evaluating our own responses to uncertainty and speculation. Human psychology exhibits well-documented biases toward both wishful thinking and catastrophic imagination that can lead to either dangerous complacency or paralyzing anxiety. The discipline of scientific methodology, with its emphasis on evidence-based reasoning and proportionate responses to uncertainty, offers protection against both extremes. Perhaps most importantly, the scientific method embodies values that may prove crucial for successful navigation of a cosmos that might contain intelligences far more advanced than our own. The intellectual humility that acknowledges the limits of current knowledge, the collaborative approach that pools diverse perspectives and capabilities, and the commitment to truth over convenience all represent human characteristics that might be valued by any advanced civilizations we might encounter. The mystery of 3i Atlas ultimately serves as a mirror that reflects our current understanding and capabilities, while highlighting the vast territories of knowledge that remain to be explored. The object's estimated mass, whether 500 million or 8 billion tons, represents a concrete physical reality that exists independent of our theories and speculations about its nature. Our task as a scientific civilization is to develop the capabilities necessary to understand that reality, whatever it might prove to be. The journey from initial detection to comprehensive understanding may require decades or centuries of sustained effort, technological development, and intellectual growth. The recent discovery of interstellar objects marks only the beginning of this process, not its conclusion. Future generations of scientists, equipped with more sophisticated instruments and expanded conceptual frameworks, will undoubtedly revise and refine our current understanding in ways we cannot anticipate. The wonder that drives scientific inquiry. The same wonder that led us to detect and study objects like 3i Atlas despite their extraordinary distance and apparent insignificance, remains humanity's greatest asset in navigating an uncertain cosmic future. This wonder motivates us to reach beyond the comfortable boundaries of current knowledge, to ask questions that challenge our assumptions, and to develop capabilities that expand our understanding of the universe we inhabit. Whether 3i Atlas proves to be a simple chunk of interstellar ice and rock or something far more significant, its passage through our solar system has already enriched human understanding and sparked imaginations that may guide our development for generations to come. The true measure of our response to this cosmic visitor will not be whether our current speculations prove correct, but whether we maintain the curiosity, rigor and wonder that make us worthy participants in whatever grand cosmic story we are destined to discover.